Welcome to This Explainer. Today, we're diving into something absolutely fascinating, the hidden economics of industrial design. Now, when we look at massive industrial plants, our brains usually go straight to the complex chemical reactions, or, the sheer scale of the heavy machinery. But what if I told you that the actual spatial layout of a plant, literally where every single pipe, wire, and steel beam goes, is what actually drives massive economic savings? Well, today, we're going to decode exactly how this works and uncover the secrets hiding right there in the blueprints. Okay, let's just jump right in. At first glance, an optimized layout might just look like a totally chaotic maze of pipes and tanks and structural steel, right? But I promise you, there is a very deliberate, highly calculated financial logic at play here. Every single placement decision is specifically designed to save money, space, and energy. So, over the next few minutes, we're going to take a conceptual walkthrough of a typical facility to see exactly how clever engineering translates into hard cash. We can break these design savings down into four main pillars. 1. Minimizing pipe runs. 2. Optimizing electrical distribution. 3. Using multi-purpose structures. And 4. Maintaining a compact footprint. So, let's start with pillar number 1, minimizing pipe runs. In plant design, shorter paths literally mean less cost. Think about the journey a fluid actually takes traveling through a facility. When engineers purposefully design the plant to have shorter paths between equipment, the financial benefits completely cascade through the budget. First off, you instantly need fewer raw materials. That means you completely avoid buying and installing expensive miles of steel piping on day one. But the crazy part is the savings continue way after construction is done. Because if the fluid doesn't have to travel as far, you drastically reduce heat loss, meaning you spend way less energy keeping things at the right temperature. And of course, shorter distances mean less internal friction, which literally demands far less pumping power from your motors. To really see this in action, think about how designers put related operational units in super close proximity. For instance, if you place a reactor and a fractionator right next to each other, you physically eliminate material waste. The output of one unit instantly becomes the input of the next, traveling just a couple of feet. Honestly, it's a pretty simple geographic decision, but it totally optimizes the fluid's journey and slashes operating costs over the entire lifespan of the plant. Moving right along to pillar 2, optimizing electrical distribution. Before we get into the layout specifics here, let's define a super quick piece of industry jargon, the MCC, or Motor Control Center. You can basically think of the MCC as the central brain, or the main distribution hub, for directing power throughout the whole plant. It takes that incoming high-voltage electricity and safely hands it out to all the heavy motors, pumps, and machines that need it to run. Now, where you place this central hub is an absolute game changer. In an unoptimized layout, your MCC might sit way far away from your heavy machinery. That means you need massive, incredibly expensive, thick electrical cables running everywhere, kind of like a giant, messy bowl of copper spaghetti. But in an optimized layout, you strategically place that motor control center near both the power grid and your major high-power users. This keeps those power lines remarkably short. Thick copper wire eats up capital incredibly fast, so keeping those runs as tight as possible, that's just brilliant economics. Okay, let's hit pillar number 3, multi-purpose structures. Basically, making every single piece of steel pull its weight. Now, what's really interesting when you look at these massive facilities is the towering steel framework housing the various tanks and columns. Notice exactly how it's designed. A single shared accessway, like a staircase and platform system where the workers would stand, is actually engineered to serve two totally different levels and multiple distinct units all at the exact same time. When you translate that physical structure into financial terms, the savings are just massive. By using double-duty frames and shared accessways, you completely skip having to design, buy, and build separate scaffolding or isolated supports for every individual piece of equipment. True efficiency here means buying and building with significantly less steel overall. The structure itself does double duty, shrinking the material footprint while keeping everything perfectly safe and accessible for the operators. Finally, pillar number 4, maintaining a compact footprint to maximize plant density. The best designers out there are always hunting for free real estate. For example, look right underneath those large elevated pipe racks carrying the colorful fluid lines. Instead of just leaving that ground space empty, smart engineers tuck necessary processing equipment and small tanks right underneath them. This tactic of nesting equipment in otherwise unused areas creates an incredibly compact overall footprint.
By tucking things under pipe racks and existing structures, you literally prevent the plant from sprawling out over unnecessary acres of land. And why does this matter so much? Well, a smaller geographic footprint means you spend a whole lot less capital on buying land, less on moving earth, less on pouring giant concrete foundations, and less on paving utility roads around the facility. It just keeps all of those foundational infrastructure costs incredibly tight.
So let's bring this conceptual tour to a close with a quick summary of those total economic savings.
To recap, our 4 foundational steps are: minimize your pipe runs, optimize your power distribution, share your structural supports, and nest your equipment. The really crucial point to take away here is that none of these are isolated design choices. Every single time an engineer places a reactor close to a fractionator or slides a pump under a pipe rack, those micro decisions compound into massive, macro-level financial savings over the entire life of the plant.
Which leads us to a pretty mind-boggling question when you step back to look at the big picture. Just how much space, material, and energy is wasted in unoptimized designs? I mean, imagine the staggering hidden costs of a poorly planned facility, the endless miles of extra copper wiring routing power everywhere, the thousands of tons of redundant steel, the daily drain of extra electricity needed just to pump heavy fluids across a sprawling site. The physical and financial waste would be absolutely astronomical if you ignored these 4 pillars. And that brings us to a final, provocative thought to leave you with today. How can these exact same principles of compact, multi-purpose design apply to your own environment? Whether you're organizing an industrial warehouse, setting up a complex server room, or honestly even structuring the workflow of your own office, these foundational rules of plant layout economics still apply. Keep related things close, share your support structures, and optimize your footprint. Look around today. You might just discover your own hidden economic savings. Thanks for joining me on this explainer, and keep optimizing.